So I believe on page 156, did we have to do the bottom two? Does that look about right? Yeah? Okay. So for the first one on the bottom, if q of x equals this function, what is the value of the derivative of q at 2? So just like some of the other questions, they're basically asking us to find a derivative. We got to know which shortcut to use. And then in this case, we're going to plug in a number. So when you look at this function, what are some things in there that might clue you into the type of shortcut we have to use? We've talked about product rule, quotient rule, power rule, trig shortcuts. Do we see anything? Quotient, because we have a fraction, definitely. Product, because we're multiplying two things together, definitely. Power, we have 2x squared, so probably have to use a power there. So we actually see 3 shortcuts for one question. How do we know which one to use, or which one is more present to use, which one's more appropriate to use? We technically are going to use all 3 of them, but we got to figure out what's the main one. What's the main shortcut that this function is displaying? Can we think about it or reason through it? Quotient? Why?
Because I feel like the f of x divided by g of x is the biggest part.
So visually, that's the biggest part, right? Okay, so the quotient rule, if it's just f of x and g of x, notice how that only applies to this part, right? You're not really including the other piece. So this is just quotient rule. This is just power rule, right? What's the whole thing? Product. Okay, so if you find yourself needing to use a mixture of the shortcuts, we have to pick the one that affects the entire equation the most. Does that make sense? Which one's the more present shortcut? So this piece is just quotient, this one's just power, but the whole thing is product. So we're going to start with the product rule, but in the product rule process, 1d2 plus 2d1, we may have to use those other shortcuts that we discussed. So we're going to start with product, but see where that leads us. All right, so let's try to tackle our derivative using 1d2 plus 2d1. So we can label this function as 1 and the fraction as 2. So the first function would just be 2x squared. And then we have to figure out d2 according to the product rule process. How do you want to find the derivative of this second piece? That's the quotient. Okay, so here's 1, and now we got to write d2, which is going to be our quotient rule shortcut, which is what phrase? Remember our low d high minus high d low, square the bottom, and away we go, or we're good to go. All right, so we'll have 1 d2. Oh, no. Low d high. We started with product rule, but now we have to go through quotient rule. All right, so low d high, and I have those switched even. What a day. Low d high minus high d low, square the bottom, and we're good to go. Are we done finding the derivative? No. We're done with the quotient rule part, but what did we say was the main derivative shortcut we had to use? Product. So this was 1. All of this is d2. We now have to add 2 times d1. Derivative of the first function using our power rule would be 4x. So something that we're going to, this is a good foreshadowing, I guess. We're eventually going to be talking about how we can bring together some of these derivative shortcuts. So we might have to use more than one shortcut for one function, and this is a good example of that. So we started with product, but in the product process, we eventually had to use quotient and power. So I know it looks ugly, and I know it looks like a lot, but this is our derivative. Okay, so now if this is the derivative of q, let's plug in 2 and see what we get. And the table at the top is going to help us fill in with these different values. So if we plug in 2 for the first x, altogether that would give us 8. And then we're going to plug in 2 for all the x's in the function notations, and then use the table to help us there. So g of 2, based off the table, is -1. F prime of 2 is 9. F of 2 is 2. G prime of 2, -1. G of 2 is also -1, and we have to square it. We then have to add the next part. So F of 2 was 2, G of 2, -1, and plugging in 2 for the last x would give us 8. So simplification. Let's see, -9 plus 2 would be -7 over 1 would be -7. And then we got to add -16. So it looks like a -16. So what are we left with? Negative 72. Good. All right, so there's our final derivative. I know it's pretty steep, okay? So you have to go down 72 over 1, but it's still a slope value, okay? So kind of involved. We started with product, we went through quotient and even power, but we have to be careful on which one we start with first, which one's the main shortcut that we have to use. We're going to see more of this in the chain rule section, okay? So this isn't the first time. You might feel overwhelmed, but that's completely okay, because it's the first time we saw it. But we're going to get used to using multiple shortcuts at once. Let's try the next one. Find the equation of a tangent line. What do we need to know? Point and a slope. All right, so let's find the point first. Find the equation of a tangent line to the graph of v when x is 3. All right, we'll find the point. If we plug in 3 into the function, we'll get 9 over g of 3, which is -3, so our overall point is -3. Let's try to find the slope, which comes from the derivative. So when you take a look at the function, what shortcut does it seem that we're going to have to use to help us? (3x divided by g of x)? Quotient. Okay, so we'll have low times d high minus high d low, square the bottom, and we're good to go. So let's plug in 3 to get our slope value. G of 3 based off the table was -3. If we plug in 9 for the next x, or if we plug in 3 for the next x, we'll get 9. And then G prime of 3 was 6. G of 3 was -3 again, and we have to square it. So -9 minus 54 all over 9. -63 divided by 9? -7. All right, so we have our point, we have our slope. We'll write our equation. Y minus the point equals our slope times x minus 3. We doing okay? That was the end of our quotient section. Low d high minus high d low. Over the weekend, I asked you to view, or not the weekend, last night, I asked you to view the video assignment for the chain rule process. And this is probably the one derivative shortcut that students kind of get tripped up on because I don't really have a good, easy phrase for us to kind of remember it by. There was someone who on the responses said that he thought of his own phrase to help him with it, and I'm not sure if it's going to help. But if we have one function inside of the other one, the chain rule process was the derivative of the outside, keep the inside, times the derivative of the inside. So he did something similar, like when I say 1d2 plus 2d1, like the d normally means derivative. He thought of d out within times d in, if that helps. So derivative of the outside with the inside times the derivative of the inside. I don't know if it helps. It's not as catchy as the other two, but if it helps him out, that's fine. If it helps you out, that's okay too. But that's what he thought of. So we're going to check out a few examples today with our chain rule. And most of us also said that we wanted more help with the trig examples based off of the last two problems from the notes. Now, before we get to something like that, though, Anuj, if you wouldn't mind, can you ask your question that you wrote on your response, if you remember it?
Yeah, so
Okay.
I was wondering, like, it seemed like in the examples, like, for all the examples, it seemed like whenever you had, like, some sort of function
Yep.
raised to a power,
Mm-hmm.
all you do is, like, you said in the video that, like, 3 was the outside, like,
Yep.
function,
Mm-hmm.
but it seemed like you just, like, kind of did, like, a weird, like, sort of power rule thing where you, like, dropped it.
Yep.
And dropped the exponent by 1.
So maybe it was my mistake for not being clear enough what or how this is the outside function. So when you take a look at this example, this was originally two different equations. Like we can label them f of x and g of x. And we got to figure out if we were to put g of x inside of f of x, this is what the ending result would look like. So if you can identify 4x plus 1 as the inside, you could say that's the g of x function. But what function are you actually plugging this into to make it look like this? X cubed, right? If you take this and plug it in here for that x, it's going to look like this.
Oh, snap.
So when I say the power of 3 is the outside function, it's actually meaning this.
That's great.
And that's when you use the power rule. Do you see it?
I got it.
You got it? Okay. So the way I explained it, I was trying not to go this route to confuse people, like to try to identify that, but that's where it's coming from. Do you see it?
Yeah, that's great.
Okay.
That's awesome.
So when I do label a power as the outside, it's actually representing x to a power. Got it? Okay. Let's go ahead and just for practice, if you have a blank piece of paper in front of you, or maybe find the back of a homework page that's empty, I just want to go through some examples before we get to some of the ones from the notes. Okay, just for practice, and we'll talk about them. Okay, let's try. And we said we wanted help with trig ones, so we'll go ahead and do trig ones. What if I had cosine to the 4th of 3x? I want to find the derivative of this function. Can we label any inside or outside pieces? Because if you read it out loud, cosine to the 4th of 3x, notice how I never said times or multiply, and I never said divide, right? So product rule and quotient rule are kind of out of, nor not necessary. Okay, so this is probably going to be a chain rule in some type. Can we identify an inside or an outside piece? Inside, outside function.
3x is the inside.
Okay, that's one inside. Because it's inside parentheses, that helps. Can we rewrite this?
Yeah.
How?
3x goes to the 4th power.
Say it again?
3x goes to the 4th power.
So, abbreviation would be cos. Okay, so cosine of 3x, cos to the 4th power. Okay, something like this. So whenever you have that power attached to the trig function, this is mathematically how it's represented, but we write it here because if I were, for instance, to put the 4 where power normally goes, it might get confusing whether the cosine function is being raised to the 4th power or just the 3 to the x is being raised to the 4th power. Okay, so we put the 4 here to symbolize the cosine part is being raised to the 4th. In other words, the whole thing is being raised to the 4th. So this is one inside function. Can we label any other inside-outside functions?
Cosine of 3x is the inside, and the 4 is the outside.
All right, so we're going to have a chain within a chain. Do you realize how you can identify 2 inside functions, but also 2 outside functions? So if you just look at the cosine of 3x part, this is the in and this is the out, right? But if you look at the whole thing, the 4 is the out, and then cosine of 3x is the in. So if you can identify multiple inside-outside pieces, you're going to have to use the chain rule multiple times, and that's when it gets a little confusing. So we're going to start from the outside and work our way in, kind of like that onion example I mentioned, or the gobstopper. We're going to start peeling away these layers from the outside in. So our derivative, we would need the derivative of the outside. So we'd bring the 4 down as the power. We're going to keep the inside, which was cosine of 3x. And if we brought the power down, the new power is 3. Okay, so this part is representing the derivative of the outside, keeping the inside. We then have to multiply by the derivative of the inside. So if you said the inside was cosine of 3x, you got to ask yourself, how are you going to find the derivative of that? Is it another chain? Is it a product rule? Is it a quotient rule? It could be anything. But it's basically asking you to find the derivative of what's on the inside. And when we looked at it a little more closely, we said it's another inside-outside property or characteristic. So we're going to have another chain rule. So to find the derivative of the inside, we're going to go through the chain rule process again. We need the derivative of the outside, which would be negative sine, keep the inside, which was 3x, and lastly, we got to multiply by the derivative of the inside, which can be just 3. So it can get a little tedious because if you think through it, we had to use the chain rule once, but in order to finish the chain rule process, you had to do another one again. So they kind of that's why it's called the chain rule. Sometimes they're going to be connected to each other, like in links. If you have to do one over again, okay, that's why it might be called the chain rule. So we can clean this up. We can take 4 times 3 times negative 1 to make a negative 12 coefficient. And we can write cosine cubed of 3x and then the sine of 3x. So this is what it might look like in a simplified form, more eye-appealing. All right, we're going to try another one. Let's try the square root of 4 cotangent cubed of 2x. We're going to try to find the derivative. Can we rewrite it, though, to help us kind of see which shortcuts we're going to have to use? Yeah.
We can put everything under the bracket in parentheses and then put it in 1/2.
Okay. So this would be, say it again. So we have 4 cotangent of 3, 2x. No, you're right. And this would be 1/2, like that, right?
Yes.
Yes. Okay. Can we rewrite anything else? Good, Anush?
I don't know if this is helpful, but like you can kind of separate the stuff underneath the parentheses. So it's like 2 times like the square root of 2x. I don't know if that's helpful.
Where are you getting the 2 from?
Like you can change underneath what's underneath the square root
Yeah.
to 4 times cotangent cubed of 2x. And then, like, since it's under a square root, you can, like, separate it, like how you would simplify a root, so you can get, like,
Oh.
4 times the square root of
Gotcha.
cotangent.
You could try that
I
way.
don't know if that's helpful.
It might be. Do you see something different, Christian?
I'm thinking we move the cube on the cotangent to the outside of the 2x, and then we group it again, so we can easily see that we have
Like
the inside and outside.
like that.
Yes.
Oh, man.
Okay. Do you know what? Anuj, just so you don't feel like doing that, I'm gonna change this to a 5. All right. Okay. So we know we can rewrite roots as powers, so we did that. And instead of having the power on a trig function, we're going to rewrite it as its own expression, okay, its own quantity, as something cubed. So let's see if we can go through our chain rule. I know it's going to be a lot. You see how many parentheses we have? It's starting to look like an onion, right? You have those different layers. We're gonna start to peel back, okay? So what is the overall outer function? The outer part, the 1/2. So if this is the outer, that means everything else is the inner, right? So let's find our derivative. We'll bring the 1/2 down. We got to keep the inside. And if we brought the 1/2 down, the new power is -1/2. Okay? So now, to finish off the chain rule, we have to multiply by the derivative of the inside. All right? So take a look at this inside part. How can we find the derivative of that stuff? So we already did the 1/2. We can ignore that. How are we going to find the derivative here? Yeah.
We're going to do the same power rule type thing,
Mhm.
where we do the exponent times the 5. And
Yep.
then we do the exponent minus 1.
Okay, so when we just take a look at the inside stuff, how we find the derivative of that would be another power rule. So the outside is this power of 3 and the coefficient of 5, and the inside is the cotangent of 2x. So we'll bring the 3 down, make it 15, keep the inside function. If we brought the 3 down, the new power is a 2. But we have to finish off the chain rule. We have to multiply by the derivative of the inside. So if this is the inside, how are we going to find the derivative of this stuff? Do we see another inside-outside part? Yeah, what's the outside? Cotangent. Okay? What's the derivative? What's the derivative of cotangent? Something negative because it's a c. Okay, something.
Cotangent cosecant.
That's the cosecant derivative.
Negative cosecant squared.
Negative cosecant squared. Okay, that's the derivative. We keep the inside. To finish off the chain rule, we have to multiply by the derivative of the inside. 2. And we're done. So we did the chain rule 1, 2, 3 times. 4, yeah, 3 times for that one. Okay, I would say this is chain rule on steroids. Okay, you're normally not going to have to do it more than twice, but it helps to see the process. If you can identify inside, outside stuff, we're going to have to go through that chain rule. Okay, so I'm hoping after doing these 2, it's actually going to make the ones that we do today a little simpler, right? Because these were, I think, pretty difficult. So let's take a look at page 163. Now that we are familiar with these 3 shortcut rules, we have the product rule, the quotient rule, and now the chain rule. These are referred to as the big 3. Okay, power rule is nice, but it's pretty simple. We have product rule, chain rule, and quotient rule to help us with more complicated functions. So when we go through some of these examples, we may have to use more than one shortcut to help us find the derivative. And this is when we have to think about which shortcut applies to the entire function itself, or at least the biggest part of the function. So if you take a look at our first one, and maybe reading it out loud would help, what are some shortcuts that you notice we're going to have to use? product because
I read it out as 5x times the square root.
you said times, right? So product is going to be in there somewhere. Do we notice anything else we might have to use? Can we rewrite it without the root? Maybe that'll help.
It's a chain,
Why a chain?
because the x plus 3 can be the inside. And
Yep.
the 1/2 can be the outside.
Okay, so we have some of those different shortcuts coming in. The question is, which one is the more appropriate one to use because it affects the entire function? Product, because you have this piece times this piece. Okay, the chain rule only applies to that square root part. So we're going to start with product, but in that process, we might have to use chain because that's another shortcut we identified. All right, so let's start with product rule. We need 1, which would be 5x, times d2. So we said we're going to have to go through the chain rule. We'll bring the 1/2 down, keep the inside. New power would be -1/2. And finish off the chain rule by multiplying by the derivative of the inside, which would be 1. Okay? Are we done with the derivative? No, because we said we have to start and finish with product rule, right? So this is 1 d2. We now have to add 2 times d1, the derivative of 5x. 5. All right. So there's our overall derivative. We're going to practice cleaning it up, making it a little bit more eye appealing. Okay. Now, if you look at the first part, the first term before the parentheses, notice how we do have a negative power. So we could move that to the bottom, and maybe you want to make it a square root again. Okay, so just the x plus 3 to the 1/2, we can move it to the bottom. Where can this 5x go? Where can this 1/2 go? Where can this 1 go? In the top and the bottom, where might those pieces be located? Okay, we're just looking at the first piece, or the first term here.
5x can go on the top.
5x up top,
2 on the bottom.
2 on the bottom, times 1, doesn't really change anything. Okay, so our first term can simplify to this. Then we have to add the next term, which is kind of simple. We'll have 5 times the square root of x plus 3. So there's our derivative. You could spend the time to get a common denominator and actually add the two together, make it one term. Sometimes you might have to do that, sometimes you might not, but I'd say this is pretty good nonetheless. Okay? Again, I can't tell you how far you have to simplify it. It just depends on the problem at hand. Let's try the next one. Maybe read it out loud, see if that helps. Can we identify any shortcuts?
Product.
Why?
Because I said it out loud is sign times.
It's not sign times, it's sign of. Okay. Quotient, why quotient?
2x plus 1 divided by x plus 3.
Okay, we definitely have a fraction, right? So quotient rule is going to be in there somewhere.
Chain.
Why chain?
Sign can be the outside function, and then the 2x plus 1 over x plus 3.
That would be the in, okay? So we got to ask ourselves which one is more applicable to use? Which one affects the entire function more? Why?
It uses like the sign function and what's the inside.
It uses everything, right? Notice how the quotient rule only applies to the fraction part, but the chain rule includes the sign. So we're going to start with chain, but in that process, we may have to use quotient. Okay, so we have to be careful on how we go through this. Let's start with chain. So we need the derivative of the outside, which would be cosine. We're going to keep the inside. And to finish off the chain rule, we have to multiply by the derivative of the inside, which we said we're going to have to use quotient rule because the inside's a fraction. All right, so we're going to write our quotient rule in big parentheses because when you use the chain rule, everything's being multiplied together. All right, so let's go through our quotient rule. We need low d high minus high d low, square the bottom, and we're good to go. So that's our derivative. It looks crazy, it looks like a lot, but we could probably simplify it to make it a little bit better. You can't really do anything with the trig function, so we'll just keep that the same. What we might be able to change is the quotient rule part. Maybe we can simplify the top a little bit. So if you distribute in the 2, we'll get 2x minus 6. And if we distribute in the minus sign, we'll have minus 2x minus 1. So 2x's cancel, we're left with negative 7 over 2x plus 1 squared. Okay. There's our derivative.
Supposed to be 2x plus 1.
Oh, I was looking at the top. I'm sorry. Good catch. Bottom squared, right? That's better. Are we doing okay? Kind of? Pretty good? We're gonna try one more. Okay, this will be the last one before we before the bell rings. Okay? Take a look at it. Rewrite it if you have to. I suggest that every single time you see a root, rewrite it. What shortcuts do you notice? Go ahead, Christian.
Quotient and the chain.
Okay, quotient because
The quotient because there's a fraction.
whole thing's a fraction. Okay,
and then
chain.
Chain because you can see at the top there's an inner portion, which is that right there, and the outer is
The 1/2. Okay, so we have two shortcuts we might have to use. Which one applies to the whole thing? Quotient, because the whole thing's a fraction. Okay, so we're going to start with quotient. In that process, we might have to use chain, but we're going to make sure we end with quotient. What you start with is what you end with. You might have to use other shortcuts in the middle. All right, so quotient rule. We have low, and then d high. So to figure out the derivative of the top, Christian said we'll have to go through our chain rule. The derivative of the outside, so we'll bring down the 1/2, keep the inside, drop the power by 1, finish the chain by multiplying by the derivative of the inside, so the derivative of 2x plus 5, 2. Okay? Now we just finished the chain rule, but we said we need to start and end with the quotient rule. So we still have more to do. This was low, d high, minus high, d low would be 1. Square the bottom, and we're good to go. All right, let's see if we can clean this up a bit. So just looking at the top portion, we can start with the 3 minus x and end with the 2, because all that stuff's being multiplied together, and then the next term comes after the minus sign. So we're going to simplify this part. I do see a negative power, so this term can become a fraction. We can move the 2x plus 5 to the bottom, and the power of 1/2 would be a square root. So the question is, where are the other terms going? Top, bottom.
2 and 1/2 cancel each other.
Okay, so if you actually do 2 and 1/2, those go away. So where does the 3 minus x go? Or x minus 3 go? On top. It's a power of 1, so it's going to stay up top. Okay? So this first part can change into this fraction. We then can subtract the next term, which would be another square root. And this is still all over x minus 3 squared. Okay, one thing I really need to stress, at least for this example, is notice how this negative power did not move to the bottom with this. Okay, it has to move to the bottom of its own term. That's why it became a fraction. Can we understand that difference? Okay, so when you do have negative powers, be careful how you turn them positively. We could keep going if we had to, because we have multiple fractions going on. You could get a common denominator, combine these two things together. Instead of dividing by this, you can multiply by the reciprocal. Okay, we still could do more, but I'm happy that we can get this far. Okay, at least for now. We'll work on the simplification. But my thing I want to make sure we can do is work through our derivative shortcuts to eventually get here. Okay, that's the big thing for now. All right, so we'll stop there for today. We'll finish off this chain rule section tomorrow, and then Thursday we'll have our practice day in preparation for your quiz on Friday.